So let me start by saying that I'm very glad to present our speaker today, Veronica Dexheimer from Kent State University. She got her PhD in 2009 from FIAS, Frankfurt Institute for Advanced Studies in Frankfurt, Germany, at Goethe University. She had several positions as a visiting professor, adjunct professor at Göteborg College first, and then she was a professor at Kent State University since 2015, I think. She is a tenure track professor, assistant professor at Kent State University. She is an awardee of NSF Early Career Award. She was working in the field of neutron stars and dense matter for quite some time. A lot of interesting results recently. So she will be talking about exotic matter produced in neutron star mergers. So with that, I'll give the microphone to Veronica. Welcome, and please, you may start.
Thanks, Igor, for inviting me. I wish I could be in Arizona right now. Still winter here in Ohio. The weather forecast for tomorrow is temperatures below freezing with snow. So today I'm going to talk about matter that we think is produced in neutron star mergers, which is very dense and hot, and what are the consequences of that. So this is the group that I've done with my students here in Kent and collaborating with the group of Luciano Rezala in Frankfurt. So, because I think probably all of you have been seeing too many talks recently discussing common features of neutron stars, instead of doing a review like that, I thought I should start by discussing a little bit of the history behind the modeling of neutron stars. So the first prediction for neutron stars were done by Landau, surprisingly enough, 1 year before the discovery of the neutron. And this is quite an interesting feature in my opinion, because you have to think that at that point, people's knowledge of the atomic nucleus was just a positive blob. And if you have something positive, which is too big, you have too many charges, and because electromagnetism is so strong, much stronger than gravity, you cannot keep it together. So what Landau said at the time is that for this to work, to have a giant nucleus, the laws of ordinary quantum mechanics would have to break down, which is quite a horrible thing to do in the 30s. So what people did is that they scratched out the date of this paper and was buried for a long time. And most people thought that this prediction was actually done 1 year later, which was not the case. And this was only discovered about 15 years ago. So a year later, the neutron was finally discovered, and then it made much more sense to have a giant nucleus because there was, in this case, the possibility of having many more neutrons and not so many protons, in which way it would work because the star wouldn't have so much of a net hadronic charge. And at this point, neutron stars, or the possibility of a giant nucleus, was not yet related to supernova explosions, which people had been observed and documenting for thousands of years, because the supernova explosions are so bright, they can outshine a whole galaxy, they can be seen with the naked eye. And in the 30s, people for the first time made this relation between neutron stars, which as being stars that remain of what happened after a supernova explosion. And at this point, the star cannot do fusion anymore because the explosion itself starts after the star runs out of fuel for fusion. Oppenheimer and Volkov were the ones that suggested that these stars exist because the way they fight gravity and do not collapse to a black hole is through a degenerate Fermi gas model. So because neutron stars is full of neutrons, and neutrons are fermions, because you cannot stack all fermions in the same energy level, you get all this extra energy and pressure that allow the star to fight gravity. Of course, neutron stars also have electrons. The thing is that they are about 90% neutrons and only 10% protons, and the same number of electrons as the number of protons. So the electrons don't contribute as much, and protons. But we know that stars are not just a free Fermi gas, because if that was the case, they would not support all the mass that we know they do. So we need to model neutron stars interactions, and the nuclear force has an attractive and a repulsive interaction. And the first person to model this in a relativistic model was Veronica in '74. And this is a still widely used model for the interior of neutron stars until nowadays. But of course, later on, people had to add modifications to the Veronica model. By the modification, I mean higher order interactions that allow us to fit better nuclear properties, saturation properties. If you just use a simple Veronica model, for example, you cannot fit compressibility and binding energy saturation that we know have specific values of some error. But the issue is that as we increase the density of stars, even at zero temperature, we have enough energy to create particles that are more massive than the nucleons, the hyperons. And the first person to model that in a neutron star was Glendelin, which is sort of the father of the description of neutron stars. And later on, people start including all sorts of possibilities. For example, we investigated also the possibility of negative period baryons. But what I want to discuss today is not that. What I want to discuss is the possibility, which is more exotic in some sense, of having quarks inside a star. And why more exotic? Because people agree, not everyone, but most people, I would say, agree that hyperons would appear at about 2-3 times saturation density. And also there's a possibility around there, or a little bit higher density for the quarks to appear. So the first time this was mentioned in the context of stars was in '69, when it was suggested that stars will have a quarkian core. A little bit later was suggested that a star could be made fully out of quarks. I'm not going to discuss this possibility today. This has some drawbacks of having a star that's purely quark with no hadronic crust whatsoever. What I'm going to suggest, if you have a quark core, but you have a hadronic crust around the star. And of course, the amount of quarks or hadrons you have, it's model dependent. But there's another possibility, a third one, in which you have a mixed phase. So you have a phase, and that's shown in the bottom star here in this slide, in which you have a mixed phase with hadrons and quarks coexisting. And the reason that this mixed phase exists and has a certain, occupies a certain region in the star is that if you allow charge neutrality to be fulfilled globally, not separately in each phase, but if you allowed quarks to be negative and hadrons to be positive, and when they combine, they are charged neutron, just by this being favored by lowering your energy, you create this mixed phase. We can extend to a few kilometers in the star, depending again on your parameters. So this was suggested by Glendelin in the 90s. Since then, other possibilities have been suggested. For example, we have investigated what happens if you consider different conservations. When you're talking about matter in supernova explosions, or right after supernova explosions, in the first minute of the life of stars, when you call the proto-neutron stars, we also have other things that are conserved. At this point, the neutrinos cannot still leave the star because the star is too hot. And in this case, we have a lepton fraction conservation too. So we also study how different mixed phases are formed in this case. But when I think about neutron stars, I always think about this kind of slices. When you have, when you look at this, usually these slices are not made in the correct scale, because the crust is more thin than the core. The crust has about 1 kilometer, while the core has about 10 kilometers. What people refer to as the crust is where you still have nuclei. And when these nuclei are dissolved, just because of the increase of density, you have just bulk hadronic matter. But of course, the interface between the core and the crust is quite complicated, because here you have still the electromagnetic force competing with the nuclear force, so you can form all these funny shapes that people refer to as pasta phases, like spaghetti, lasagna, and so forth. But I'm going to discuss the interior of stars, and more specifically, the possibility of hyperons appearing, baryons that are more heavy because they also contain strange quarks, and eventually quarks. I don't want to discuss too much about the model that I'm using to create this equation of state that we're going to use for the neutron-star mergers. And the reason for that, otherwise I spend a whole hour talking about it instead of showing results. So within this, this setup, we can have hadrons and leptons and quarks coexisting within the same model. So this model was made to reproduce nuclear physics around saturation, but also has inputs from astrophysics, and specifically in the quark part of the model from lattice QCD. So the way in which you can have several degrees of freedom, different ones within the same model, we have to find a way to switch them at some point. So the way this is done is through the effective mass of the particles. So because this is a chiral model, instead of just having bare masses, vacuum masses that are modified by the medium, in chiral models, the mass is generated by the medium. So the mass is generated by interaction of the scalar mean field of mesons, which also has isoscalar component, but also isovector component and a component of hidden strangeness, which is important for the interaction of the hyperons. And you can have small bare masses here, but the last terms are the ones that I'm concerned about, because if we add a coupling constant here that's very large, whenever this field phi is large, the mass of the baryons becomes too large and the baryons disappear from your system. And this will happen at large densities and temperatures. And for the quark is the opposite. When phi is large, getting close to 1, because again, the coupling constant is large, the effective mass of the quarks will be too large and they disappear. So in this way, this field phi becomes the order parameter for the confinement, and you can switch the degrees of freedom. And this is interesting because it allows you to have different kinds of phase transition. Usually if you plug two equations of state together by hand, you always get as a result first order phase transition. But with the setup, you naturally get crossovers out, depending again at your temperature or density. We also use a potential for this field phi, which was modeled in a way mimicking the behavior of the Polyakov loop, but we also have terms that depend not only on the temperature, but also the chemical potential. And in this way, we can draw a phase diagram for QCD that looks like this. So here I'm showing temperature, and in the x-axis, chemical potential, but you also can think about this as just density, net baryon density. So as you're going to the right, you're going to the interior of neutron stars where matter is more compressed. So here in the lower left part of the diagram, you have hadronic phase. On the top right corner, you have quark phase. And I drew here two different lines. So the black line corresponds to isospin symmetric matter, where you have more or less the same number of protons and neutrons as the case that are expected to have happened in the early universe, or what we reproduce in particle colliders. And in the line in pink corresponds to neutron star matter, which is matter which has to be charged neutral. And for the neutron star case is in chemical equilibrium with respect to the weak force. And when you think about neutron stars, we have here in the very bottom, in the crust of neutron stars where you have nuclei, this overlaps with the world where we exist, where you have nuclei here in the very bottom, but neutron stars also have a bulk hadronic matter component, and also we think that it might cross to the very right side here of the diagram where you have quark phase. These bubbles I just add here for covering more or less where you think that these different conditions exist. Neutron stars we know are here at very low temperatures. Supernovae we have more or less with more results from different simulations, but for neutron star mergers there are less simulations, especially containing quarks where we did the first one, including first order phase transition. So at the end of my talk, I want to come back here to discuss in more details why I think neutron star merges sphere goes right here in this position where it is. Actually, right now I'm only talking about a circle. This will have to wait until another talk for the sphere in which you have, because then you have to study 3D phase diagrams. I'm not going to do this today. So right here, I'm just reviewing a little bit more because I showed in the beginning of the talk these two stars without and with the mixed phase. So in the phase diagram that I showed you, the pink line here is now shown in green, is a line in between two phases. But if you allow the mixed phase to exist, this line becomes a black region, shown here. Which one is really the case? Well, for that will have to do with the surface tension of quark matter. The surface tension is incredibly high. You really can build a wall between the phases and you don't have this mixed phase. But if it happens to be lower, then you have the mixed phase. In this mixed phase, you can construct mixed quantities, like some sort of mixed baryon density. Because we're talking about first order phase transitions, and I'll talk a little bit more in the end of the talk why I think this, why I'm studying first order phase transitions to begin with. Whenever you have a first order phase transition, it means that the first derivative of your potential has a jump. So in this case here in the green situation on the right plot, you have a jump in baryon density from the left to the right. But if you allow this mixed phase to exist, you don't have a jump anymore. You have a continuous increase in density as you go right. And how do they look like when you're looking at the composition of matter as a function of chemical potential or density? And again, here going to the right in any of these figures, you'll be going inside your star. So beginning at the left, we start as a result of the Karamin field model. We get neutrons, protons and electrons, some muons, and then we start with hyperons. The thing is, if you allow these quarks to appear, this deconfinement will suppress the other hyperons. You end up just with a few lambdas before the phase transition. And then on the other side, you have quarks down, up, and later on some strangeness because they have a larger bare mass. What happens if you allow this mixture of phases? Well, you end up with this region in which you have a combination of hadrons and quarks coexisting. This looks like a very small region, but you have to keep in mind that the conversion from chemical potential to the stellar radius is not linear. So a small region here in chemical potential actually corresponds to a large region in radius that can extend up to 2 kilometers of the star with this parameterization that I'm showing you here. But when you're talking about how dense a star can be, so going back here, how far do you go to the right in either of these plots inside a particular star? Well, my answer is it depends on how fast the star rotates. Because all neutron stars rotate, some of them rotate quite fast, thousands of times per second. And this is pretty much works like a centrifugal force. So the faster the star rotates, smaller is the central density, up to the point in which it can start shedding mass. The fastest pulsars observed have about 700 hertz. So we start here right in the middle of this figure. And you have to think that usually, I'm not talking about special cases in which the stars are creating matter from a companion. Usually stars lose energy over time because it's radiating and it rotates slower over time. So you can think about going left in this figure as a function of time. So in order to create this figure, first of all, you cannot use the simplified version of general relativity, which reproduces spherical stars, because as stars rotate, they get deformed. You have to remember that even their planet is a little bit deformed. So what happens is that if you're considering stars that rotate about 700 hertz, they already contain hyperons. You have to rotate much faster than that for hyperons not to appear. And what happens is, as the star starts rotating slower and slower, you can increase the central density to trigger this threshold after which quarks appear. So this case here, I'm showing a massive star, but is a cold star. If you add temperature, the quarks appear at a much smaller density. But the thing is, although these kind of diagrams are very nice, this is not accessible at all. From many things that we can measure right now or measure in the future, measuring what is the central density of the star is the hardest one, even indirectly. So we have to consider that until very recently, all that we knew about anything in the universe was what we could learn just looking, observing the light.
Veronica,
yeah.
We have a question here, brief question. Pavel, please.
What about gravitational phase separation, like water vapor, that the phase with higher energy density will fall down towards the interior?
You're talking about what I was talking in the slide about finding out what's the central density?
Yeah, sorry, because the, asking through chat is delayed in phase compared to your progress. Apologies.
Yes, so matter is much more compressed as you go towards the center, but how exactly could you use that to measure?
Rather than the phases being, a mixture, is that water, water goes into the ocean and the vapor is above. So why not the same with the two phases for?
Are you talking about the mixed phase?
Yeah. Why wouldn't it separate?
I mean, it is separated. Even without, you have to think about it, even without the mixed phase, you have more quarks, which is the phase which is favorable at large densities, than the hadrons. So this will be like just hadrons and then a little bit more bubbles of quarks.
Okay, so just, okay. Good.
I'm just talking about simple structures, there will be bubbles.
Okay.
Then as you go more to the quark phase, you have more like a Swiss cheese kind of structure of quarks, some hadrons inside. Of course, we know that in reality, we create much more complicated structures than bubbles. And many people are actually doing research in this nowadays, how because of this, all this energy balance, and some people that are actually here listening to, work is something equivalent to pasta phases for the quarks.
So it's like pasta, okay, I think that's.
But I'm just talking about something much more simple, but that's what you have.
Okay, Veronica, there is another question since we already interrupted. Go ahead, Efrain. Efrain? Do you want to ask now?
Sorry. Hi, Veronica. I think that at the beginning you were connecting the mixed phase with the global neutrality. This is true, or that was my understanding?
Yes. So when you I don't remember what it was anymore. So when you required that each phase is individually conserving whatever quantity you're talking about, you don't create these mixture phases. So to create these non-congruent scenarios, you need to have more than one conserved quantity. Of course, the baryon number is always conserved, so I'm not counting that. So when you have an extra one, besides baryon number, is when you create these non-congruent phases. And of course, the more you add, the more complicated it gets, more than those global conserved quantities. We only investigated one extra, which was lepton fraction. But people like, for example, Uli Heiss in the past have investigated what happens with strangeness too. Strangeness is some quantity that can be conserved locally or globally. We haven't done that yet. But this is what creates mixture phases.
But it means for the electric charge, you know, that
yes.
you need
and some of them are long range, like electric force and electric charge conservation, but some are not, like lepton fraction. And then you get different features.
Only if you then have a charge conservation for the three phases, you can produce the mixed phase. That's what you mean, no?
Yes.
Okay.
Okay, I suggest we move on. It was not as short as I expected.
And by the way, now for the remaining of the talk, I'm not going to talk about that at all, because when you're talking about trying to find more about the interior of neutron stars and using gravitational waves, which is I'm going to talk next, we're aiming at the largest effect that we could get. And then so from now on, I'm just going to stick to normal first order phase transition to see if that's good enough to cause, you know, any effect that we can see and use to understand the interior of the star. Any mixed phase, and the more extended the mixed phase, the worse, would just hide any signals that I'm going to discuss, you know, and then you have to see how extended these mixtures are and how much they will hide what I'm discussing now. So until recently, we could only learn about the universe using light. Of course, there is some information from the neutrinos, but it was not the majority of information we were getting. And even for light, it's complicated because most of the light is blocked by our atmosphere. Here on the ground, it can only have visible light and radio waves. For everything else, we have to go to space, which makes everything more complicated and more expensive. But fortunately, in 2007, we measured the first neutron-star merger, a little bit after the black hole merger started to appear. There might be more neutron-star mergers that we have already detected, but this one became very famous because it was also observed using light. So we can be 99.99% sure this was a neutron-star merger, not black hole merger. So when stars are in closed binaries, they can inspiral towards each other, and the more they inspiral, more energy they lose through gravitational waves, and the closer and faster they get closer to the point that they merge, and they eventually become a black hole. Why necessarily a black hole? Because neutron stars have more than one solar mass each, and when you add two, unless you're very lucky and you know you're in the right interval, because neutron stars cannot be much more massive than two solar mass, you probably become a black hole. In order to produce a neutron star, you have to merge white dwarfs, or at least one white dwarf will have to be involved probably. But the thing is that in this neutron star merger, we did not observe the second part, what happens after the merger, what's called the post-merger signal. And the reason for that is because here the amplitude changes, the frequency changes, and the detector are not sensitive enough at the moment to measure that. There are exceptions. If you have a merger happening very close to us, there is a possibility that it could, even with the current equipment, observe the post-merger signal. So what you can do is you can produce these waveforms like the one that LIGO observed using hadronic models. And I'm just showing here a very large overview of an old paper from Luciano's group in which many different hadronic equations of state were tested. And I just highlighting the fact that you see everything you hear. You see all sorts of behavior and use different equations of state. Going from the top to the bottom, you're using different equations of state, and going left to right, you're using different masses. We know that stars that are in binary systems that are going to merge in a reasonable amount of time are not very massive. So notice that they are merging stars around the 1.2 to 1.4 solar masses, but no more than that, and that's the reason. But what about quarks? So here you see that when you use different hadronic equations of state, you have different signals all over this waveform. What we found is when you are investigating two equations of state, one that allows the quarks to appear and one that doesn't, the change in the signal is in the post-merger part. So for this, we use the 3 version of the Kármán field equation of state. Why 3D? Because these are not in chemical equilibrium. So besides temperature and density, you also have to use charge fraction. And then we, in collaboration with the group in Frankfurt, solve their fully general relativity hydrodynamics code and obtain these waveforms that I'm showing here. And what I found out is when the quarks are allowed to appear, they appear in the post-merger part, and I'll discuss this much more in detail later. So they affect this right side here of the signal, and they force the star, or they trigger this collapse to a black hole much earlier. So the signal is shorter, but not just that, but the frequency is modified. And the phase difference for the frequency of the two signals are shown here in the bottom. We investigated this for 2 different cases, one in which are merged 1.4 solar masses, 2 stars of this mass, and 1 or 2 stars a little bit more massive, 1.45. If we merge stars that have less mass than that, we don't form enough quarks fast enough to see an interesting signal. If we merge stars with masses that are larger, the stars, hypermassive star that you form become a black hole too fast, and you cannot have an interesting signal. So this is the ideal scenario, which is not far from what we think the star that was observed that I discussed in the first slide, the star merger was. So now I'm going to discuss more about the simulation. So what happens is when you merge 2 neutron stars, you form this hot ring around the center, where more or less this original center of the neutron stars were. And this is shown here. In the left, you'll have the largest temperature in yellow. And on the right part of each panel, you have the amount of quarks appearing. And as I said before, because this model allows for crossovers at large temperatures, the quarks start to slowly appear even in the hadronic phase as the temperature goes up. But it's a very small amount of quarks. You have to keep in mind that this is a log scale for the quarks. And this is very common in simulations. You always form this ring. What's different here, this ring allows some quarks to appear. But what's interesting, as you let the evolution of the simulation takes its course, at some point, you will reach a region in which dense enough and hot enough for quark matter to be formed. So you're crossing that first order phase transition line. And when you do, because of the softening you get when you cross the first order phase transition line, there's a local collapse in which matter gets much more dense and much more hot very quickly. And that's what you see here, this very bright spot appearing with lots of quarks and very hot. See how I'm doing on time, sorry. Okay, still have time.
Don't worry too much about time.
So before showing you this phase diagram or how the neutron star merger appears in the phase diagram, I'm going to discuss just a little bit the background that I use. So the background just gives you the idea, the amount of quarks that you have where you are. So what we plotted here is the 2D carrier field equation of state. Why 2D? Because it's a phase diagram, and if I would be too crazy to try to show this in a 3D one, that's coming. So I'm just choosing a random charge fraction here. It's a very low one. So mainly neutrons or neutral quark matter. And what you see here is that at 0 temperature you have just hadrons or just quarks, so black or white. But as you increase the temperature, you still start having more quarks in the hadronic phase, and you're going to start having also more hadrons in the quark phase. The reason I don't really see this is because of the logarithm scale that is shown. And eventually, as you go up, you're going to reach a place beyond 160 MeV where everything is light yellow. So now we have to make a choice. Or we show the complete simulation at a specific place, or you show one moment in time and the whole simulation. So that's what I'm doing first. I'm choosing 5 milliseconds for my time frame after the merger, and then I'm showing you everywhere. So the blue curve, the blue area here is the result of this 3D carrier field table in the general relativity simulation. And what we see is here on the top middle part, you have the ring. So you have this larger temperature region. Remember the ring that I said is formed around the center in the beginning of the merger. And our collaborators refer to this as the wing of the swan. And then here we have already passed the time where you can form the quark core. So here, when you cross the phase transition, because of that collapse, matter gets very hot and very dense very fast. And then after you cross the phase transition, you have this more or less constant temperature region. So we refer sometimes to this as the swan plot. But this was one option. There are many other options of things we can show. An interesting one, if you want to see the time evolution, is focusing on the largest temperature or largest density in the merger. So just keep in mind that we are not tracking one position. It's more or less the same position because these things change over time. So as the circles get darker, time is evolving, and the hottest part was the ring around the center, which has some intermediate density. But then when you create that hot spot in the center, you jump to a much denser and hotter part here on the right top part of the diagram. And I said that we're also following the densest part, which is pretty much close to the center, which just gets denser and hot as you go by. And the reason I like this is because here you can again see how hot and how dense you get in the merger. So you can get to about 65 MeV temperature with something like 1450 MeV. And if you go back to that phase diagram that I showed you, more or less what I had, guessed my bubble before neutron-star merger. But you still have to be careful because neutron-star mergers, they are hot, and as I'm going to discuss later, they have an entropy which is comparable to low energy heavy ion collisions. So I'd like to see, this overlap here, which is kind of a complete way of showing our knowledge of high energy. And it's nice to see how they overlap. But you have to be careful because neutron star matter, usually people refers to, is also in chemical equilibrium. Supernova are not in chemical equilibrium. They are almost isospin symmetric. They have a very large hadronic charge fraction of around 0.4, depending on the time and place you're in the simulation. But for neutron star mergers, we wanted to investigate, is this really what people consider neutron star matter? It's more like supernovae matter. So we drew phase diagrams investigating charge chemical potential and charge fraction. So I'm just tracking the maximum temperature and densities. And what we found out, so as the symbols are getting darker, is time going by. So as here you see, these orange circles represent the ring, which was very hot. And the diamonds represent the center of the star. And as you can clearly see, the charge chemical potential is increasing towards the center of the star. But after you reach that first order phase transition line, which is shown here in the top part of the left figure, your charge chemical potential becomes much smaller in absolute value. And that's quite understandable because usually the charge chemical potential is much smaller in the quark phase and the hadronic phase. And that has to do with the imbalance of different particles with different isospin, which is much smaller in the quark phase than in the hadronic phase. So charge chemical potential, you can think about the difference in chemical potential between neutrons and protons are up and down. It's much smaller in absolute value in the quark phase. And also I wanted to investigate what's the charge fraction throughout the merger, because I wanted to see how close you could get to supernovae or heavy ion collision conditions. And I was very surprised to see that it's never very large. It's much more like a neutron star conditions around 0.1, maybe reaching close to 0.15. And the reason for that is that this quantity never increases, because when it was about to increase in the very dense and hot region, because of the phase transition, again, you go back to quark matter, in which you have a very low charge chemical potential, absolute value, and then you have, again, you decrease your charge fraction. So we never reach the conditions from the other situations that we're investigating. So I have here a simulation. I just have to stop sharing the screen, but when I upload the video, you can just click on the YouTube simulation and you can see the video. And now I have to open it separately. Let me just open the video. There it is. I'm going to start sharing this. Okay, so you should be seeing the video now showing the merger. So first you have two individual neutron stars which get closer, start deforming each other, and then they merge. And here, now I'm showing the quark fraction in the left part of the screen, which increases as the hypermassive star gets denser and hotter. And here you can see the temperature too. First the yellow forming sort of a ring around the center. And then in the very end, you can see the hot part in the center. And of course, you know, lots of matter is expelled, but I'm concerned about is the hypermassive stars formed in the center. Let me stop sharing this. Go back to this. I hope you can see the slides again. Let me know if you cannot.
Everything's fine.
And instead of discussing the video, I prefer just to freeze it in time and look again at those 5 milliseconds after that I showed this one plot before in the phase diagram. But here, instead of looking at the phase diagram, we're looking at the merger itself. So these are coordinates, like looking at the merger from above. And here in the right part of the left figure, I'm showing temperature and the left entropy per baryon. And what you can see is that you have some hot regions, but a much, much hotter and tropic region is the center, where you have crossed the threshold for the first order phase transition, in which can reach temperatures close to 60 MeV temperature and 5 entropy per baryon units of the Boltzmann constant, which again are conditions similar to the ones that are expected to be reached in the beam energy scan at RIC. But what was more interesting for me was studying the strangeness in this merger. So as I said before, in this equation of state, you form only, or you create only a few hyperons before the confinement. But that was, and all the other hyperons are suppressed by the quark matter appearing. But this was at 0 temperature. At large temperature, and here we're talking about tens of MeV, you could generate a lot of hyperons in the hadronic phase. So that's why the strangeness is large here. I'm showing on the left the strangeness fraction, and on the right, just the quark strangeness fraction. So what I find out is strange all over, but what happens is that the strange hadrons are replaced by the strange quarks in the center in such a way that the strangeness doesn't change across the first order phase transition. But on the right side, you can see that if you're just looking at quark strangeness, there's very little before the first order phase transition, but there's a lot after. So this is very interesting, but again, you have to keep in mind that we haven't measured the post-merger part of the signal. Hopefully we will at some point in my lifetime, in our lifetimes. But there's more that you can learn from merger. There's much more that you can learn in a merger. I'm going to talk very briefly about a second feature that mergers have, which is that deformation that happens before the merger in the part of the signal that I actually measure. And that gives us information about the tidal deformability, because larger stars can be more deformed. So there is a relation between the tidal deformability that we measure and the radius. So the tidal deformability, which is a unitless normalized quantity, has to be less, or different groups have different calculations, but most groups would agree that's below 1,000 or below 800, depends on who you ask. But there's lots of work being done on this area. And what has been observed is this relation between the tidal deformability and radius of these intermediate mass stars with around 1.4 solar masses, which is what we think merge more or less. So this was done with simple hadronic equations of state. So if you get an equation of state, let's take this green one, for example, select the star that has 1.4 solar mass, put its radius here, and check against tidal deformability. You see that if you do this for many different equations of state, you get some sort of line. So this gives a hint of this strong relation, and a very important question I have to ask, is this a universal relation? Because in general relativity, using general relativity can find all these universal relations, which are to some extent equation of state independent. So this was a very important work from Caroline that appeared 2 years ago, and we decided to also investigate that with our models. We cannot, or there's no point in using any quark matter model at this point because we're talking about intermediate or low mass stars, in which case you cannot really form quark matter because it's not dense enough. So we use different hadronic models. So a hadronic version of the chiral mean field model together with different hadronic models or relativistic and allow different degrees of freedom to appear like the hyperons. And what we found out, if you use this, we started investigating different couplings, and we found out that if you use this interesting omega rho, so it's a vector isovector mixed coupling that was proposed by Horowitz and Pikarovitz about a decade or two ago, maybe 1.5. What we found out is that if you increase the coupling, and we're just looking at the radius of a particular 1.4 solar mass stars, the radius changes with this coupling. And what I found out is that if you plot this against tidal deformability, just for this specific mass of star, instead of having a point here for each equation of state, you have a whole line here. So that tells us that we can not only use nuclear physics to learn more about astrophysics, but we can go the other way and use astrophysics to learn more about nuclear interactions. So from this plot here, it seems that if the tidal deformability is low, going below 1,000 or below 800, or some people say below 600, these points towards a very strong vector isovector coupling. And just so you have an idea, this is not just a random coupling we're testing. We found out that if you're comparing your results at low density with effective field theory, which is a very, very reliable theory at low densities, which is the densities we're showing here in the X range, and we're looking at the pressure for neutron matter only, we find that for different models, whenever we increase this coupling, and these are showing the dotted lines of different colors, we are even in better agreement with effective field theory. And there are actually many other reasons to point towards this kind of coupling, like predictions for neutron skin, for example. So here's my conclusions. I think astrophysics is an ideal testing ground for nuclear physics, especially because I think we can go the other way and learn about nuclear physics from astrophysics. And neutron-star mergers are very unique events that create unique conditions that are different from everything else that we had already studied. And now, in addition to learn using light, you can learn about space using gravitational waves. But in order for this simulation to tell us more about, to teach us more about nuclear physics, we have to use, it's important that you use models that are realistic. And by realistic, I mean, if you're going to go to very high densities and very high temperatures, your model must be relativistic, for example. Otherwise, you're going to get into trouble with the speed of sound being much larger than the speed of the light. And also use degrees of freedom that we expect to appear at large densities and temperatures, like, for example, the quarks. And more merger data is coming in the following runs of LIGO in the following years, and hopefully we will have many more mergers of neutron stars to learn from. Thank you.
Thank you very much. It was an excellent presentation. So I'll clap for everybody. We have some questions. So I guess the first question comes from Konstantin Maslov, please. Hello? We cannot hear you. Yeah, go ahead.
Can you hear me now?
Yes.
Yeah, great. Thank you very much for a nice talk. So my question is related basically to all these figures of the thermodynamic quantities during the merger, which were plotted on the T versus mu B axis, right? So my main question is, what are the maximum densities reached in merger in terms of density units, maybe saturation densities or Fermi's to minus third or something like that? Could you tell us?
This is an excellent question, but the answer is not so easy, because we're just talking about 10 milliseconds here, 50 milliseconds, but in each millisecond frame, things are very different. In the very end, right before collapse into a black hole, I think we reach densities of around 10 times saturation density. But that's right when it started collapse into a black hole.
So 10 times, you say, the maximum one?
Yes, but that was the maximum. Where I think we also reached 1500 MeV for the baryon chemical potential.
Thank you. And I have one more question, if I may.
Go ahead.
So on the next, or slide 22, I think, there was a plot of the charge fraction over the mu B, right? What is charge fraction here? Shouldn't the merger
So the amount of your
neutral as well?
So there's the amount of your baryons which are charged. So it's the hadronic charge
no
fraction.
leptons.
If you have just neutrons, it's 0. If you have half neutrons and half protons, for example, it'll be 0.5.
Yeah. So, but in merger matter,
you do have the leptons that balance,
there, right? So
I'm just talking about hadronic charge fraction. You have the leptons that will fulfill charge neutrality.
And what we can deduce from this
is that in neutron stars, the charge fraction will be determined by the condition of weak chemical equilibrium. So the hadronic charge fraction in neutron stars increases with density, and usually, this is model dependent, you can reach maybe 0.15 in the center of a neutron star. In a supernovae, this is much larger, because you have to think that you began with the same amount of protons and neutrons are created during the explosion itself and neutronization reactions. But it's still not that small. So when people usually simulate supernova conditions in your equation of state, or the people call proto-neutron star matter, they usually fix the charge fraction to about 0.4. Also, if you're talking about energetic heavy ion collisions, where the nuclei really cross each other and there's so energetic that there's no stopping, the matter you create will always be isospin symmetric. So your charge fraction will be 0.5. But if you have some stopping, then it matters which charge fraction you have, because then you have some stopping. And in that case, when it matters and you go to low energy heavy ion collisions, you can reach something like gold, lead, something like 0.4. So in principle, when people were starting to talk about mergers a few years ago, they're talking about conditions being very similar to heavy ion collisions or supernovae. But now we found out that they are not exactly the same. In this sense, they're more like neutron stars than heavy ion collisions or supernovae.
Okay, we have the next question. Jamie Stafford, please.
Hi, Veronica. Thanks for the nice talk. So I was just wondering about this mixed phase that you were showing with the quark core in the middle and the mixed phase moving out. Can we think of that as really a density where we're sitting along this first order phase transition line, where you have this coexistence region moving through the phase transition, or is it something else?
Yeah, so the line disappears at all, in a sense, when you have this mixed phase. and it becomes a region. And in a sense, it's kind of bad because it's really, if you're thinking about, you know, observing it, because not only in the laboratory it'll be complicated to observe, but also in astrophysics it'll be complicated to observe because any signal that I showed, for example, will be washed out by this mixed phase. So it's really a region, as is shown here, and it can actually be exaggerated. This is not exaggerated, it can be bigger than this.
Okay, thank you.
Okay.
And because you know, not only your density, but your pressure increases throughout this mixed phase. It's really going to, you know, not sink or float. It's going to be occupy a specific region in the intermediate layer of the star, if you think about an onion structure, in which the pressure and all quantities increase slowly.
Okay, I don't see any questions from the audience, but I do have a question of my own. When your charge fraction during the evolution is changing due to weak processes, that will be accompanied by the neutrino production, anti-neutrino production. Are those neutrinos playing a role in the changing the pressure of the system, temperature, anything really? Or you're simply ignoring them?
So I hope that I can give you a good enough answer because you're asking about things that really depend on the general relativity code that is used to simulate the merger. So this code that I think I wrote down the name, that was written by the Frankfurt group, they have a neutrino leakage scheme. So they are taking the neutrinos into account. Is that what you're asked?
I think so, but I'm just not sure if I understand regarding their contribution to the actual equation of state.
Oh, they contribute very little. If you're asking just about the pressure added by the neutrinos, is very little in comparison to everything else. What really makes a change is that if you have a lot of leptons, you have a lot of, to compensate, if you have a lot of hadronic charge fraction. That imbalance between the hadrons is what really changes things a lot, not the direct contribution from the neutrinos.
I see.
One question here.
Go ahead.
Okay, I'm assuming talks about quarks, up and down is obvious, and talks about strange quarks. Fine. What about charm quarks?
So there was a very interesting work recently from Eduardo Fraga and collaborators.
That's why I'm here.
They studied the possibility of charm quark in neutron stars. And they found out that, I think it was the first principle calculation they did. They contribute, there couldn't be any contribution because the energy scale is just not as nearly enough for the charm.
So it doesn't matter for charm, right? This one. Thank you.
You only have up, down, and strange.
Okay, I believe we ran out of questions. So if there are no more questions, I will be wrapping this up. Thanks again, Veronica, for a great presentation. Interesting physics described here. I think everybody learned something. And that's all we have for today.
Thank you.
Thank you. Thanks. Thanks, everybody.